Tonight on Antenna, the search for gravity waves. Scientists from both hemispheres collaborate in a quest to discover the one outstanding prediction of Einstein's theory, which is yet to be tested.
Traditionally, astronomers have looked at nearby events, like solar flares, with optical telescopes, picking up the light waves given off by the hot gases. More recently, astronomers have turned to radio waves and have seen further out into space. But light and radio waves are both electromagnetic effects, and they are not the only forces at work in the universe. So they can show us only part of the drama. Other parts of that drama, caused by other forces, are invisible to us, hidden behind the veil of dust and gas clouds. But now scientists are hoping that a new window on the universe is opening. They hope soon to be able to see the one overwhelming force in the universe, which until now has remained completely invisible to us, but which is so all-pervading that it determines the shape of space itself. It is the force which creates stars and ignites supernovae, but can equally crush them down to an invisible black hole, sending out waves of energy across the universe. That force is gravity. And it is gravity which holds the key to the first milliseconds of the universe's existence, further back than we have been able to reconstruct information from even the most powerful particle accelerators, and which will help us to understand how structure first formed in the universe. One of the things that's exciting to physicists and mathematicians like myself about gravitational waves is that they allow us to see out into the universe in an entirely new way. We've always seen objects out in space by detecting the light, radio waves, and other electromagnetic signals that they emit. What we've not been able to do is to see the force which is ultimately responsible for causing all this activity. It's gravity that shapes the universe and is the driving force behind everything that we are familiar with in observational astronomy. To see what I mean with something more familiar, look at this Newton's cradle. Without gravity, the ball wouldn't fall. It's the force of gravity pulling the ball towards the Earth that starts Newton's cradle off. We can see and hear the balls colliding just as astronomers can see the light coming from stars, but they do not directly see the gravity that drives the system. If we could pick up gravitational waves, then we would be looking at the ultimate cause of all the activity in the universe, not just the results. And for the first time, we will be able to see disembodied waves of gravity, that force that was first understood over 300 years ago by Isaac Newton. Although it was Newton whose laws of gravity first explained the workings of the solar system, his picture of gravity and the universe were different from today's. For Newton, gravity was part of a clockwork-like rigid place where time and space were inflexible. In this universe, matter moved according to exact laws governed by the even ticking of time. Time in Newton's universe was separate from and unaffected by the movements in physical space. But at the turn of this century, the even ticking of time and its neat separation from space ended. The cause? A young patent clerk from Germany called Albert Einstein began publishing a series of papers which together argued that time, space, and matter weren't separate at all, but intimately affected each other. A proposal which has fascinated scientists like Paul Davies ever since.
Einstein totally transformed our understanding of space and time. Going back to Newton, there was this idea that space and time are simply there, like an arena in which the great drama of nature is played out. But we now think of space and time after Einstein as being not so much the arena, but as part of the cast in this great drama. They are themselves players. That is, space and time can change and can move and have their own dynamics. It's not just a sort of rigid backdrop in which things happen.
The most remarkable consequence of Einstein's theory of the link between space and time is that time is flexible. Time, according to Einstein, can stretch or contract, run faster or slower, depending upon how fast you're moving and on the strength of the gravitational field around you. In Einstein's universe, time was no longer absolute or separate from matter. Time had become a flexible part of space-time. Now, the thing about Einstein's theory, like many great theories, is that people didn't always agree about what it meant. It took a while before all the ramifications of Einstein's basic idea could be worked out. Now, Einstein challenged Newton's ideas of stars and galaxies moving around in a vacuum of space without disturbing it. According to Einstein's ideas, as they move, they actually bend space and time. Another consequence of space and time being bendy is, well, like any other flexible medium, any disturbance will cause ripples or waves to travel along it. So as stars move around, bending space and time as they go, they will also send out waves. And these waves are gravitational waves. Imagine space crudely represented here in 2 dimensions by a rubber grid. The mass of the ball in the center distorts or bends the space around it. In this analogy, space is bent, so nearby objects must follow a curved path. That, in effect, is gravitational attraction. And just as the movement of the ball creates ripples in the rubber grid, a star moving through space will generate disturbances in the fabric of space-time. These are gravitational waves.
Only a year or so after he had formulated the general theory of relativity, he realized that there was the possibility of these wave-like disturbances passing through space. And there was a bit of controversy about whether these waves were all in the mind, that is, that they were just mathematical artifacts, or whether they represented a real physical disturbance. It soon became clear that there really were physical waves corresponding to gravitational ripples. And I think it is now the outstanding prediction of Einstein's theory which is yet to be tested, because many of his other effects that he's described, the peculiarities in the motion of Mercury, the effects on clocks of gravitational fields and so on, these things have been tested pretty thoroughly. And the one major prediction which he has made, which is the gravitational wave phenomenon, has yet to be tested. And I think this would be the final piece in the jigsaw of what is probably the most beautiful mathematical theory that has ever been constructed.
From the theory, scientists were convinced that gravitational waves ought to exist, but no one had ever detected any. The first person to try to do that was the American physicist Joseph Weber.
I think Joseph Weber must take the credit for pretty well single-handedly taking the subject of gravity waves from just a theoretical prediction into the world of practical physics. But by about the 1960s, he actually had a detector up and running. It was just a bar of metal that was suspended in a very delicate way and would vibrate if a gravity wave passed by. And he got a couple of these things going, several hundred miles apart, and he looked for shakes, judders, little disturbances in these 2 bars, and he looked for coincidences between them.
Weber found coincidences and announced to the world that he was seeing gravitational waves. But not many agreed with his results, and so his findings were clouded by controversy. Then, in the 1970s, came a stroke of luck. Astronomers had been searching through the veils of gas and dust when one of them came upon the remains of one of the universe's more violent events. He found what were the remains of 2 supernovae. Supernovae are stars, spent of fuel, which are blown apart by shock waves as they collapse under the weight of their own gravity. In many cases, what remains is a neutron star, an incredibly dense mass just a few kilometers across. What he found were 2 neutron stars trapped in orbits around each other. And this binary star system offered tantalizing evidence for the reality gravitational waves.
So we've got 2 of these neutron stars, orbiting around each other very rapidly like this and emitting gravity waves like crazy. Now, by fortune, one of these neutron stars is a pulsar, which means it's spinning itself very rapidly, and as it spins, it emits radio waves a bit like searchlight beams. So as it sweeps around past the Earth, each time you see it, you get a blip, 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 and this is a very, very accurate clock. And so what you've got is a binary star system, two neutron stars orbiting around each other with a clock. Now, you can monitor that clock using a radio telescope and follow the antics of this system as it orbits around, and you can see the very slight distortions to space and to time which Einstein's theory predicts as this clock moves in and out the gravitational field of its companion star. And you can measure these effects so accurately that you can actually see the decay of the orbit of this system due, we believe, to the emission of the gravitational waves.
So we seem to have confirmed that gravitational waves do exist, and we know some pretty good places to look for them. But that still leaves us with the problem of actually detecting them. The gravitational waves that come to us from a binary star system are ripples in the gravitational field. And as they wash over the Earth, they will alter gravity very slightly. Now, this slight alteration will cause a vibration, an actual physical vibration, and that's what we intend to measure. The problem is, the world is full of vibrations. Your house has been continually disturbed by aeroplanes flying overhead, even distant binary stars. Just imagine trying to pick out one tiny vibration from all that disturbance. So what astronomers have to do is to build a detector that shields out all the vibrations they don't want and enables them to pick out the one tiny vibration they're looking for. It's like a camera, which has to shield out all the stray light in order to get a clear image of the one thing it's looking at. And this is precisely what scientists at the University of Western Australia are trying to do. They've built a vibration sensor, 1,000,000 times more sensitive than a radio antenna. The heart of their gravitational detector is a carefully suspended bar of the rare metal niobium, which when disturbed produces a pure sound wave. To work, the bar has to be isolated from outside vibrations, so that any gravitational wave that passes through the Earth will disturb it, making it resonate. But the detector's builders, led by Dr. David Blair, have no illusions about their chances of actually detecting a wave.
Well, if I tell you how difficult it is, you'll probably believe it's impossible. The size of the vibrations produced by a gravity wave are as small compared with an atom as an atom is compared with the tallest building in the world. It is a minute vibration. The problem is that we have to isolate against other sources of vibration. We have to isolate against the vibration of the ground, which is vibrating a billion times greater than the vibrations that we're trying to detect. Then we have to be very careful of other sources that can make things move, like magnetic fields and electric fields, all sorts of things.
But once the outside vibrations have been minimized, those inside the detector itself still have to be dealt with. The first step is to seal the entire detector in a vacuum. But this still leaves vibrations from the detector's own atoms to be minimized. So the entire detector is cooled with liquid helium to minus 269 degrees. At this temperature, the interfering vibrations of its own atoms are reduced almost to zero. So any vibration which strikes the bar will make it ring. And even the faintest ring should then be picked up by the arrays of sensors. When a gravitational wave passes through the laboratory, everything in the room will be distorted in the same way, including time, which makes it extremely difficult to sense the wave passing through. However, the niobium bar, isolated as it is from everything, should pick it up and even be able to measure its strength. What is trapped is an after effect, an echo of the ripple in space-time. Precisely engineered as it is, the resonant bar antenna has yet to detect a gravitational wave, and its chances of doing so are limited. Because it is only waves from particularly powerful events that have enough energy to be detected above the ever-present background vibrations. Within the Milky Way, such events are uncommon, maybe only 2 or 3 each century. There are, however, millions of galaxies in the universe, each generating gravitational waves from black holes or neutron stars. In theory, our planet should be regularly bombarded by these more energetic waves. As clever as a niobium bar detector is, to listen into the continual gravitational reverberations from the wider cosmos, a new and extraordinary scientific project is planned. A leap beyond even the niobium bar. This is Wallingup Plain, an hour's drive north of Perth in Western Australia. And here, amongst the creatures of the Australian bush, the next step in the search for gravitational waves may take place. It has been chosen as one of 4 or 5 gravitational wave observatories to be constructed around the world. At the moment, the Australian scientists are engaged in the slow process of trying to raise $90 million to turn the bushland into a new observatory. What they're planning is a new generation detector. Based on work pioneered at Glasgow University, it will be 1 million times more sensitive than even the best detector we have at the moment. The heart of the new system is not a rod of metal, but a shaft of light. This is a laser interferometer, a configuration of beams of laser light bouncing off mirrors and into sensors, all precisely aligned and focused. Here at the Australian National University's Department of Physics, they're trying to develop a system that will form the heart of the Wallingup Observatory. Looking like a giant capital L, the proposed observatory will sit in Wallingup Plain, listening in on the universe. Each arm is a giant tube, 3 kilometers long. At their junction, the control center will house a powerful laser. The light generated by the laser will be split into 2 by a special beam splitter, each half projected along its tube at the speed of light. The idea is that the laser beam is bounced back and forth many times between the 2 mirrors. The 2 halves of the beam of light are then recombined. Normally, the interferometer is adjusted so that the light waves from each half of the laser are perfectly symmetrical and cancel each other out. If a large enough gravity wave passes through the observatory, it should squeeze and stretch space-time, first in one direction and then the other. This should change the distance each laser beam has to travel by a minuscule amount. In that case, when the beams of light are recombined, they will fail to cancel each other out, and so some light will be allowed through. The detector will then register the intensity of the light, evidence of a passing gravitational wave. Assuming, as always, that waves can be found to minimize all other vibrations.
Some of those we can do relatively easily, such as putting it in a vacuum, which will get rid of the sort of noise which comes from clapping, and sound noises, or noise speaking. Then fluctuations which occur in the vacuum due to the gas itself come about because of changes in temperature. Then, of course, there is a noise which is always there, and that is noise due to the seismic background, just vibrations coming through the Earth. Now, to get rid of the seismic noise, you have to isolate the mirrors from the outside source, and that's done by a series of masses and springs, and eventually the mirrors hang on wires like a pendulum.
What the Australians hope to do with their observatory is to answer some of astronomy's most fundamental questions. If we can detect gravitational waves, and more importantly tell where they come from, they should give us our first accurate measurement of how fast the universe is expanding. At the moment, all our theories about the universe and its ultimate fate, such as whether it will continue to expand forever or collapse back on itself, are hampered by not knowing to a factor of 2 how fast the universe is expanding. Such fundamental research will come from the use of gravitational waves to observe binary stars, exploding supernovae, and the hitherto invisible formation of black holes.
What it lets us do is to look into the moment of formation of black holes, to actually observe black holes forming. We'll be able to see into the depths of events that otherwise are completely impossible to observe.
In order to realize the full potential of gravitational astronomy, scientists around the world need to create a global network of 4 or 5 similar observatories. By comparing the results from them, scientists will be able to pinpoint the actual sources of the gravitational waves. But the technology behind all these hopes is expensive, and funding is far from certain. Britain's funding, for example, is at the moment seriously in doubt. As the Research Council's budgets are slashed, projects like this are in grave danger of being scrapped. And if they are, then Einstein's last prediction will not only remain unverified, but much more than that. We should be turning our backs on a new window on the universe.